To start by addressing a mistake that I made yesterday. So I'm just pulling up the notes, looking at this example here. Okay. If I look at when we found the range for the y of t, for the parametric equation for y of t, we said it was 1 to 9 exclusive union 9 to 33. It's incorrect. Mr. Kulik just made a mistake on how he was thinking about the problem. So what I did is I kind of sketched a graph of, this is a ty of t axis. So this is what we have. So notice we do have an open circle here at the point -2, 9. But we have some other point over here that uses the y-coordinate 9. So 9 is used in the range. The answer there should just be 1 to 33. So I just wanted to make sure I came back and pointed that out before we got too deep in here, that I did, Mr. Kulik boo-booed that one because he wasn't thinking about it as a quadratic, as a parabola. If it was a linear thing, we would have had that issue, but because this thing is, thanks, Benj. Natalie. Okay. All right. So for today, let's start with some questions. I would think that we probably have some. I know that, again, what we did yesterday was pretty challenging typically for the first time seeing it. So if you guys got some questions, I'm happy to spend a few minutes here handling that stuff. Anybody would want to start? Blake. 20. Sure. So here it says eliminate the parameter and find the domain and range of the resultant function. So we'll start by isolating the t in the x equation. And then we'll take that value or that equation in terms of t and substitute it in to the y equation. So when we do that, we get 2 over 27 x squared minus 1. So far, so good? Okay. To do the domain, I'm going to be looking at the function x of t equals 3t, defined on the interval from 1 to 6. If I look at the function x of t, what type of function is that? Linear. Very good. Since it's a linear function, all I need is the endpoints to figure out the range of that function. So if I think about the graph of this function, so my range for x of t is 3 to 18. Everybody's okay with that? I sketched a little picture there to justify it. So all that tells me then is the domain for my function, my Cartesian function, is also 3 to 18. Blake, so far so good?
The domain?
Uh-huh. For the Cartesian is 3 to 8.
Yeah.
Which comes from the range of the parametric equation for x. Nat?
How did you get the 1 and the 6 that you put into the x?
There, I'm just using the endpoints of the function.
Oh.
Right? Since we're only defined from 1 to 6 on t, means that I just have like a segment, right? So all I need to do is find the endpoints of that segment for a linear function, and that'll be enough to give me the range because it, you know what I mean?
Yeah, okay.
Sure. All right, let's do the range now. So we have y of t is equal to 2/3 t squared minus 1, where t is defined from 1 to 6. So, we start the same way. What type of function is y of t? Quadratic. So in the case of the quadratic, we care about the endpoints and the vertex. So I'm going to do y of 1. I'm going to be doing y of 6. Uh, 36 divided by 3 is 12, times 2 is 24, minus 1 is 23. And then the vertex is going to be at 0 over 2 times 2/3. So still just 0.
Wait, so what is that vertex equation again?
Okay. So yesterday we had that for a quadratic function, f of x equals ax squared plus bx plus c. The vertex is negative b over 2a, comma f of negative b over 2a. So I started just by finding the x coordinate, or the independent variable, the input for that. Since in this case it's really a t coordinate. But here, what do I notice about 0? Zero is not in our interval for t, so guess what? It doesn't matter. Really what we have, if I were to graph this, so I have, oops. Here's our quadratic, and then like the vertex would be over here. Right, so since that vertex isn't inside of the range, I don't need, or inside of the interval for my parameter, I don't have to worry about it. Is that okay, Blake?
Yeah, I get where.
Okay, so we'd say the range then for y of t is really just negative 1/3 to 23. Oops. Any follow-ups on this one before we take the next question? So that was a good one, Blake. Yes, sir?
I guess I'm just a bit confused. So when you actually found the domain for that, I forget why you use the actual range for the for parametric function.
Sure.
Instead of,
So this is the way to think about it. The x-coordinates are coming from, the x-coordinates for my Cartesian function are coming from the x of t parametric equation. The inputs for that are t, but the outputs for that equation are the x-coordinates, right? So the domain for my Cartesian function is the output of my parametric equation for x, i.e. the range for that function x of t.
Okay.
Right?
Okay.
Does that feel okay?
Yeah.
So again, it's tricky because like you have to step through like, okay, so the output, you have this extra lurking variable, this parameter t, that is the independent variable. So like the input for all of these parametric equations is t, but their output are y coordinates or x coordinates respectively. So like the outputs are always going to be either parts for the domain or range. Does that feel okay? Okay. Alex, I think I saw your hand earlier. Sure. So we start the same way. We're going to start with the x parametric equation and get that equal to, or get the t by itself. So we'll subtract 2 from both sides and then divide by 3, or I should say negative 3. So far, so good? Okay. And then I'll take my parametric equation for y, and we'll just plug the value for t into that. And then when I make a common denominator and combine my like terms there, so there's my Cartesian equation. Feel okay? Okay. So the domain, we're going to be looking at the parametric equation for x. So x of t equals negative 3t plus 2, where t is defined for all real numbers. Alex, if I look at the equation for x of t, what kind of function is that? Linear. And since the domain for that linear function is all real numbers, what does the range also have to be? So the domain for my function, my Cartesian function, also has to be all real numbers. Does that feel okay? All right. We do the same thing with the y of t. What type of function is y of t? Okay, and the domain for that linear function is all real numbers, so the range for that must be also all real numbers. So the range for my Cartesian is also all real numbers. There wasn't much to do on that one, which is okay, right? That's a relief sometimes. But good to talk through it still, right? Who's next? Zach?
Can you do 26?
Sure. Let's go over here. So 26 was this. Okay. So hopefully you remember that, like, when we have one of these triggy ones, we're not going to try to do this algebraically to start. So I'm going to go ahead. I have to put my calculator back into parametric mode because I had to change it out for another class. But I'm just going to graph this here and take a look at what we got. Oops. So if I take a look at this, what does it appear that I have here? Circle. Great. And what two pieces of information do I need to describe a circle? The center and the radius. Very good. So if I look at this particular circle, the center is at?
The
Origin, and the radius is? 3. Okay. So from the graph, we have a circle where the radius is 3, where the center is 0, 0. So as we mentioned yesterday, the equation, or the Cartesian equation for a circle, x minus h squared plus y minus k squared is equal to r squared, where hk is the center and r is the radius. So if we take what we had observed from the picture, we have that x squared plus y squared is equal to 9. What we need to do now is just to check this to make sure that this observation is supported by our parametric equation. So what I'm going to do is I'm going to take my value for, or the way that my x's are generated from the parametric equation, plug it in for x, and the way that the y's are generated and plug that in for y, and check to make sure that still gives me 9. So negative 3 cosine t squared, negative 3 cosine t times negative 3 cosine t is 9 cosine squared t. Similarly with negative 3 sine t squared. Feel good? Yeah. I notice here that we have a greatest common factor of 9, so I can factor that off. And hopefully at this point you recognize cosine squared plus sine squared is 1. And 1 times 9 is certainly, or 1 times 9 is certainly 9. So that is my Cartesian equation. And I guess if I wanted the domain and range for this, I could just read it directly from the picture since we have that. So that the x is going from negative 3 to positive 3, and the y's are going from negative 3 to positive 3 as well. So the domain and range are both those. Remember, we're using brackets there because the endpoints are included, right? The negative 3, 0 is a point, 0, negative 3 is a point, 3, 0 is a point, 0, 3 are all points on our circle. So on these ones that have the trig component to them, you're going to go from the graph directly to your equation based on the form of the circle and then check it with the parametric rather than going from the parametric and eliminating the parameter like we were doing in the previous ones.
Right. Thank you.
Yeah. And these could get much worse if we had done conic sections before this point but we haven't, so they'll all be circles. Oh, fun. Who else had their hand up? Alyssa, was it you?
Yeah, can you just
Yeah.
explain how to set up number 6? I couldn't figure out
Sure.
how to-
Oh, well, I would say I wouldn't even do this as a calculator problem per se. I would just do this as an aside, or just, I mean, I would use my calculator, but you don't really even need to do that. Oh, I definitely don't need my calculator to do this. So we have a TXY table here. So my values of T are this, right?
You just substitute the T in for...
Yeah, so like,
Yeah, okay. Thanks.
yeah, no problem. And you just grind through this, and these are all just unit circle results. You could type in your calculator also, but since the sine and cosine are just unit circles and we're using multiples of pi over 2, those are all unit circle values that you could look up off your unit circle, or if you have your unit circles pseudo-memorized. The quadrantals are usually easy because it's just like remembering where it is on the x or y axis. Alex, did I see your hand? 38? Yeah, sure. So for 38, essentially all we're doing is the same thing we did on 26. So again, we're just starting with my equation for a circle, right? Oops, I guess I'll put those in. Is that so far okay? Okay. And if you remember when we did the parameterization on 26, we saw that, let me scroll back to it. That basically this gives us the radius, or the coefficient gives us the radius, and the radius is going to be the coefficient. And since it's a circle, the x is just cosine and the y is just sine. So all I need to do here is going to be radius times cosine t, and then radius times sine t. And if you made both of the radii negative, that would be fine, or if they're both positive, that would be fine. They're both equivalent. And there are more than one parameterization that you could use on this, but this is the most obvious one to do. The last thing we need to do is come up with an interval for this parameter. We need it to be the whole unit circle, so it should go from 0 to 2 pi. And if you had both endpoints closed, that's okay. Or if one of them was only one of them would be closed, that would still be okay, because remember 0 and 360 are the same point on the unit circle. But you couldn't have both endpoints open and still be correct, because then it would be a circle with one open point at the r comma 0. But there's lots of different ways you could write that. And if this number, or if the endpoint was bigger than 2 pi, that would be fine. You know, if it's 0 to 7, it'd just be like a circle, and then it'll retrace a little bit more of the circle, which is fine. Or if it was less than 0, that's fine, but you need to at least have 2 pi worth of distance on that interval for the parameter. But like what you picked for that, really flexible, because all it's going to do is just like copy over what it's already done. You just need to have at least 2 pi length. Yeah, no problem. Others. Nat? 23, you say? Okay, sure. And this one's a little bit tricky because the x parametric function for x, I should say, is not linear. So just eliminating the parameter in general is potentially kind of a problem. Right? We noticed that. And this, I think, is the first time this has happened to us. We didn't see an example like this in class. So maybe it's unclear what to do. What I would do in this case is I would just start with the y coordinate instead of the x and eliminate or isolate the t. And then we'll go back and plug that in for t into my equation for x. Do I want to do that or not? Let me think for a moment. I guess it doesn't really do me a lot of good. So I'll just write it like this, I guess, for now. Is that okay? Let me double check on to see the directions say. It just says calls it a resultant. Okay. So what I'm going to do now is I'm going to get the y by itself. Is that okay? So I'll start by multiplying both sides by -9/2. So far, so good. Then I'm going to square root both sides to get rid of the squared. Remember, when I square root both sides of an equation, that creates a plus or minus. The square root of 9, I can take that out and make that 3. And then I can subtract 4 from both sides. So that's that. And Nat, looking at the answer in the back of the book here, it seems like they rationalized the denominator here inside of this radical. I mean, you can do that if you want. It's not, I wouldn't mark it down if you didn't. So I think that's where this becomes 3/2 and this becomes -2x. It's just them rationalizing the denominator, but like, don't feel like, I don't care if you don't do that, to be honest with you. Now we have to worry about the domain and range part, which is also kind of tricky. So let's do the domain piece here first. So for the domain, we have to consider the x coordinate. which is negative 2t, where t is defined from negative 4 to 3. So again, what I care about are the endpoints, and because this function is quadratic, I also have to worry about the vertex. So my endpoints is negative 32, and then negative 18, and then my vertex is going to be 0 divided by 2 times negative 2. So that's 0 is the t coordinate for the vertex. And I notice that, yes, that is inside the interval for my parameter, so I do care about the vertex here. So that gives me 0. So the range for the parametric function for x is going to go from the minimum of these three values, that's negative 32, to the maximum, that's 0. So that in turn gives me the domain for my Cartesian equation. So far, so good? Okay. Everybody else, if I lose you or whatever, holler at me, right? We're still doing okay, though? And then the range, same idea, but we're working with the y coordinate here, which is 3t plus 4, where t goes from negative 4 to 3. So here, we notice that the y of t is a linear function. So all we really need to care about are the endpoints. So we have negative 8 and 13. So y of t's range goes from negative 8 to 13, which gives me the range for my Cartesian function. So starting to feel a little bit more comfortable. I know that yesterday is a tough day, right? I tried to make sure I went pretty slow so that we are able to kind of process what was going on, but usually a night of homework and getting some questions answered makes a big difference. Are we feeling any better on this? Is it getting more comfortable? Okay. Last call on questions. Okay, very good then. We're going to do section 10.2 today. Here we're going to be looking at some like story problem kind of applications for this, or for these parametric functions. And one of the natural extensions to parametric functions is dealing with two-dimensional motion. So imagine like you have like a cannonball and you load it into a cannon, you fire it, and you're trying to figure out the position of that cannonball some time into the future. That's a natural extension to a parametric function where the position of the cannonball dictated by x and y is a function of time, right? That's how motion typically works. So we have a natural extension of these parametric functions into physics, specifically kinematics, the study of motion. So those of you that are in a physics course, some of the things that we do here in this section will feel familiar, which is great, right? Anytime we double dip between classes and you're the beneficiary of that double dipping, that's nice. All right. So we have two basic equations for motion. So we have a position function and we have a velocity function. In these positions, we have like S is height, G is the gravitational constant, or those of you in physics, this is acceleration due to gravity. V is, well, I guess this is vertical velocity because really this is one-dimensional motion, what we're talking about here. I guess I'd try to be clear about that. So imagine like you drop something and it just falls straight down. That's the kind of motion that we're describing right now with these equations. Oh yeah, and T is time. And typically, in this class, we're going to work in English units. So in English units, 1/2 gravity becomes -16. Or just gravity in this equation becomes -32. Those of you in physics also know gravity is -9.8 meters per second squared. Or if you want to be super precise, 9.81. I think there's not a lot of need for most things that we would do to beyond 2 significant figures or 2 decimal places of accuracy on something like that, but who knows, like if you're doing something very precise, could be useful. So let's look at an example here quickly of how we can use this. And rather than copying down this example in words, I'm just going to open up my Word file and copy and paste it. So I'm just kind of dancing in place for a second while I find what I'm looking for. So many pages. There we go. All right. So a ship stranded in the ocean. On top of the bridge, 80 feet above the water, a distress flare is shot straight up with an initial velocity of 32 feet per second. Provide a graph of the flare's height against time and find the height of the flare above water at the following times. So, I want to find the height of the flare above the water. If I look at the previous two functions, which one do I want? I want the first one, which is a function for height. So before I can graph this, I'm going to need to fill in the initial velocity, V naught, and the initial height, S naught. Jillian?
Where did you get 16?
Well,
Oh.
right. That's just me putting the G, 1/2 G in. Nat. Yeah, sure. No problem. So what is our initial velocity? $72. What's the initial height? 80. Everybody's okay with that? So notice that this is not a parametric function here. This is just a Cartesian. So to graph this, I'm changing my calculator mode back to function mode. Since the motion here is one-dimensional, there's no need to use a parametric. So there's that. The window, X is representing time. So I don't know, 0 to 10 seems appropriate. Y is representing the height of the flare. Well, 0 to something. It's going 80 up. I don't know, I'm going to guess, or it's already 80 feet up in the air. I'm going to guess 200. I don't really know, I'm just a guess. And then let's hit graph. Not too shabby, Mr. K, for just a guess. So there's that. Everybody's okay? If I want the values at, or the heights of the flare at 1, 2, 4, and 5 seconds, I'm just going to go press second and graph and look at the table. So at 1 second, it's 136. At 2 seconds, it's 160. At 4 seconds, it's 112. And at 5 seconds, it's 40. And just read that right off the table. What's the other way you could get those values? You just plug those numbers in for t, right? Just do it by hand on your calculator each time. But, yo, this took 2 buttons for me to press to get all the answers all at one time. I like that way. But, you know, maybe a little on the lazy side, but that's okay. I prefer to think of it as efficient. Jillian.
Can you start me back to the table?
Yeah, I just press second and then the graph button, and that opens up the table. And typically your default table setting is the table step is 1, starting at 0, and it should just open up right to it. You don't have to do anything else. Unless you wanted like weird values like t is 6.3 or something, in which case you could plug those in then, or you do some other thing using your calculator. But
I think you can just put in like 6.2 on your X value and it'll find it.
Maybe not.
Not here. What you can do is if you press the vars button and go to the y vars, pull out the function and pick y1, you can do like y1 of 6.2, and it'll plug it in and evaluate it for you. So that's a useful shortcut. And the nice part about doing that, Blake, is if you press second and enter, it'll just give you the thing you had before, and you can update it to something else. And just press enter again. You don't have to go hunting through all those menus.
So is that under the vars menu?
Yeah. So vars and then y vars for things that you've got in the y equals menu. And then depending on the mode your calculator's in,
Yeah.
you'd pick from the appropriate menu. So if you're in function, you'd pick a function. If you're in parametric, you can only evaluate one parametric equation at a time. It can't give you an ordered pair back. You have to do like the x parametric equation for x and then the parametric equation for y separately, which is kind of a hassle. But yeah, again, just talking about saving some time. So 1D motion doesn't need to be done as a parametric equation. If you wanted to do that, though, could you? Sure. Okay. So to do that, what I would do is I would call this t, and then the next one is negative 16 t squared plus 72t plus 80. So it's the same picture, right? Where all I did was make my x-coordinate time. But if I look at this picture, the same picture I had from the Cartesian form, what's misleading about this picture? Does this actually describe the motion of the flare?
No.
No, right? This is not the motion of the flare. The flare doesn't go out and down. It just goes straight up and straight down, right? So what can I do if I wanted to actually get something to give me the actual motion of the flare? Parametric can do that. So what I'm going to do is I'm just going to fix the x-coordinate at some value. I'm going to pick 1 for the sake of argument. And I'm going to change the way it graphs. Instead of giving me a straight line that stays there, I want to do this little guy that's a tracer, just for you guys to see what's going on. Let's hit graph now. That little tracer is actually tracing the motion of the flare there. How neat was that? And I think you can do that if I go look at the options, or if I press enter again. Let's do that one. This one, it doesn't even draw the line. This is just what the flare is doing. Pretty neat, right? Which is intuitively, like, that describes exactly what you see the flare doing if you're watching as a side. Pretty neat. Okay, so two-dimensional motion, not necessary that we use a parametric equation. However, using a parametric function to describe this one-dimensional motion can give us a graph that really resembles what you'd actually be seeing in real life, where the flare just goes up and straight down, which is neat, right? Pretty cool. Okay, what if we want to talk about two-dimensional motion then? Here, it is necessary to use a parametric function. I'm going to put in a parenthesis there, just so it's quite clear that the only thing being operated by cosinus t. Well, I guess I just do that. That'd be enough. And I guess I'm going to call, I don't want to call this f. I'm going to call it s of t. And I should probably call that vx. Okay. So here are our two-dimensional motion equations. I have one for position, one for velocity, just like we had in one dimensions. However, each one of these are defined with a parametric function. What else do you notice here? What is this symbol? The magnitude of a vector, right? So remember that our vector v is here. Our initial velocities are represented as vectors, but really we just care about the magnitude of the vector. You might have to find the magnitude by hand, or it might be essentially given to you in the problem. But that's a nice little piece to remember. All the rest of our variables mean the same things. So position is s, velocity is v, time is still t. So S naught is initial velocity. And then I guess we really should maybe call this like V naught, magnitude of V naught, because those are our initial velocities. Maybe I'll put that on there. So let's do an example here and see how this differs. Okay. You hit a baseball at 3 feet above the ground with an initial speed of 135 feet per second at an angle of 62 degrees above the horizontal. Will the ball clear a 15-foot fence that is 300 feet away? If yes, by how many feet? If no, how high up the wall will the ball hit? So the baseball players in the room, this should be very interesting, right? We're hitting dingers. Or trying to anyways. We'll see. So if we think about, like, from a physics standpoint, what's going on. So basically we want to find something like this, right? You guys buy that? Okay. So Are we looking to find position of the ball or velocity of the ball? To answer this story problem. Position, right? We want to find where that ball is. Does it get over the wall or past the wall or whatever? So let's start filling in our parametric equation. So what is our initial velocity, or the magnitude of our initial velocity here? 135. And the angle is 16 degrees. So that's our first equation. Then we have negative 16t squared plus magnitude of initial velocity sine t plus initial position. So our initial velocity still 135, angle still 16 degrees. What was our initial position? 3 feet off the ground, right? So if the y is basically at 3. Everybody's okay with the setup here? So let's talk about what we want to figure out, right? Basically, I want to know the time when the ball gets to the wall, because I can then take that time and plug it into the y of t to figure out the height of the ball when it reaches the wall and compare that to 15. Is everybody cool with that? To get that time when the ball reaches the wall, I'm going to use that the wall is 300 feet away and figure out how long it takes the ball to go 300 feet in the horizontal direction. That is, in the x direction, so I'm just going to solve that equation for t. Everybody feel okay with what I did there? Notice when I'm typing this into my calculator, I forgot to type write the 135. I just wrote 15. I'm going to use the fraction command, so I don't have to worry about parentheses in my denominator. Uh-oh, that doesn't seem right. What's wrong with my calculator? I'm in the radian mode because we were graphing last class. Thank you. Good call. So I'll just change that to degree mode and do it again. So I get about 2.31 seconds. So then I'm going to just do y of 2.31. So I can plug that in by hand, or as we pointed out to Blake, we can just have the calculator evaluate this for us. So if I do vars, y vars, parametric, and I do the y1 of t, and the t I want to use is that thing that I just got out. So I have that it is, oh, Boise, that doesn't seem right. Oh, that's why. Ha 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 ha! Mr. Kulik, you are stupid. Why is Mr. Kulik stupid? Well, he didn't type his function into his stupid calculator. He just started going. That's why he's stupid. You ever make mistakes? Happened to me. Everybody's okay though with what I'm doing? You'd stop me if you weren't, right? I'm going to take your silence for yes, Mr. Kulik. I would definitely do that. Oh, interesting. I was hoping that would just do that for me. Well. So I get 3.51. So did the ball clear the fence? Nope. It hit the wall at 3.51 feet above the ground. Okay. Is there a way I can have my calculator give me a super accurate picture of what's going on here? So even before I start doing anything algebraically, could I know the answer of whether the ball is going to clear it or not? Heck yeah. So we have the equation for the motion of the ball in 1. So let's see. I don't know. Baseball players, how long would like a line drive-ish baseball stay in the air?
Like 4 seconds.
Okay, 0 to 4 sounds good for T. The X range, 0 to, well, it's got to be over 300, so I'm going to do like 350 or something. Go by 50s. And the Y, well, again, we're going 0 to, line drive probably gets what, maybe like 50 feet up in the air or something at best. Right, 16 degrees is a pretty low exit angle for a baseball. That's pretty line drivey. 50 feet off the ground. For something that's maybe a home run-ish. It's probably not unreasonable, baseball players. I don't know, I'm just kind of guessing. So I do that. There's the motion of my baseball. Now, would it be nice if I could actually get the wall to graph in here so we could see what's going on? Heck yeah. Can I graph a wall? Heck yeah, I can. So the wall needs to occur at 300, right? That's the x coordinate. It's 300 feet away. And then to get the wall to go up 15 units, I'm going to do 15 divided by my max T. So let's see, where was that? That's at vars. And then window. And I go over to this one that says T slash theta. And I want T max divided by T. Nope. Sorry, times T. Ah! All right. If I graph now, there's my wall. Whoop. So if I go in and let's change this one to just be the little tracer. Here's the baseball. Oh no, the wall came in second. Boogers! I should have put the wall in first. You guys get the idea though, right? I wonder if I can. I don't know if there's a way for me to reorder the order which it graphs without having to recopy everything. I don't think there is. Ugh. We'll do better next time. All right, everybody feel okay with that though? All right, let's do another example.
That's a quick question.
Yeah, for sure.
For the first part when it says the y1, for that equation, is it just 135 times sine 60 degrees plus 3? Are you just putting that whole equation in?
Yeah, so that's just all of, that's the y equation. Just, it keeps going off the screen.
Okay. And then why do you have times t on it?
I had the T here. I missed copying it.
Okay.
Yep. Thanks, Alyssa. Again, if you catch me making typos, holler at me, or even if I do something you don't understand that could be a typo, you know, like Mr. Kulik gets excited and forgets to write things down. Enzo.
Where do you put the 2.31?
So we're just plugging that into T in the y equation. So I just did y of 2.31, and I had the calculator do it for me. So once I had typed in the equation into the y equals and gotten the graph, I can do vars, y vars, and then parametric, and pick y1 of t, and then plug the 2.31 into that. Or you can do it by hand. That's fine too. I just did it on the calculator because it's like, saves me from making a typo. Only have to type it into the graph correctly once, and then after that, the calculator will plug the stuff in for me. So I don't have to, you know what I mean? Is that cool? Okay. All right. We'll do another example. Oh, there it is. My man Jeff hits a baseball at 3.5 feet above the ground with an initial speed of 141 feet per second at an angle of 24 degrees above the horizontal. Will the ball clear a 20-foot fence that's 400 feet away? If yes, by how many feet? If no, how high up the wall will the ball hit? This is essentially the same exact question, right? Everybody agree? Or no? I'll take from your silence that that's a yes. So let's just do this all on the calculator here real quick. This time, Mr. Kulik's going to not muck it up. That's 400. And that's 20. And he's going to just type that one in down here so he doesn't have to move it. Haha, calculator, I'm going to outsmart you this time. You think you're smarter than me, think again. There we go. Change my window there a little bit. We gotta make that 450. And this is a little bit higher, you know, like a little bit more pop fly-ish. So I'm gonna probably bump that up to 100 or something. And I might make that 6 seconds now instead of 4 seconds. Again, a little bit longer in the air. I'm just guessing though. There's my wall. There's my shot or my ball. Looks like we got a dinger on the hands, folks. Cool. So to actually get the value there, we need to see the height of the ball at 400, or when it gets 400 feet away. So we need to first calculate the time it takes to go 400 feet. know where that y of whatever is coming from there. That's in my way. So it takes 3.1 seconds to get to the wall. And then I just need to vars, y vars, parametric. Then I did y3t is what I did. So I'll plug that into there. So it gets 27 feet. And that's greater than 20. So we got a dinger. Woo! Jeff, you're a beast. Because the dude's name was Jeff. Right? Everybody okay? Here's a more interesting question, though. Assuming that there were no obstructions in the way, how far will that ball travel before it hits the ground? So this is the reverse situation, right? We're going to solve for t using the y equation and then plug that answer into the x equation, right? So what height will the ball be when it hits the ground? 0, right? So there's my equation that I'm solving. How do I solve something like this? Quadratic formula, right? Negative b plus or minus the square root of b squared minus 4ac divided by 2 times a. Again, to do something like this, I'd recommend using that fraction command on your calculator. I'm going to have to do 2 of these. So I have a negative answer. Well, that doesn't seem very, very helpful to me. Although maybe not surprising if I think about what's going on. Why shouldn't I be surprised that one of the answers was negative? Well, if you think about it, we're here, right, at 3.5. So if I draw the parabola, one end of the parabola is going to be in the negatives, since the initial height was at 3.5. So not surprised that one of my answers was negative. Doesn't mean I did anything wrong, but clearly not the one I want, right? So now I just do x of 3.64. So I think I did that in x3. So I get 469-ish feet. Everybody okay with that? Are we almost out of time here? Well, we probably won't get to answer this today. Somebody needs to remind me to answer this next time. But in the meantime, you can think about this same situation with old Jeffy there. Assuming there are no other obstructions in the way, how was the furthest distance away from your starting position that you could put that 20-foot fence and still have him clear the fence? Like, how far away could the fence been and still have him hit a home run? You can think about that for next time.
I'm just trying to put this in my calculator so I know how to do it.
Okay, one second. I want to turn off my recording so it doesn't record our whole conversation.